Okay. We'll go from current slide. Now, I'm sort of guessing, I know where some people are. This is terrible that this happens, but probably with all the snow we had on Tuesday, people went out and started skiing and they weren't used to it, so they probably wrenched legs, and broke bones and stuff. So hopefully some will be hobbling in later. But fortunately, got all the snow cleared. The highway was perfect, so glad y'all could make it. All right. Any questions from anything we did, a week ago or at least, Any questions? None? All right. Where we left off last time, we were talking about these identities, and all of these were very familiar with us, I hope, by now. And if not, get to know them, okay? I think what we were doing, we were talking about the Pythagorean identities, and I think I went through all this last time when we had these identities. Did I show you how you could get from this one to that one, this one to that one? Did I show you that? Y'all remember? No? You really only need to remember that one. And the rest of them are easily derived from that. So let's take that first one. Let me get my pen set up. Okay. Sine squared theta plus cosine squared theta is equal to 1. Everybody agrees. That's easy. Remember that. Always remember that. For any given angle theta, this is always, always, always true. That's what makes it an identity. Now, what if we were to divide everything on both sides of the equation by a cosine squared theta? Legal in most states, right? The only time when it's not legal is when cosine is 0, and we're just going to exclude those values, okay? Now, what do we have? What's sine squared over cosine squared? Say again? Tan squared, right? Tangent squared. And what's cosine squared over cosine squared? 1, okay? And what's 1 over cosine squared? Secant squared theta. And isn't that exactly what we have here? They write it 1 plus tangent squared is secant squared, tangent squared plus 1, secant squared. Same thing, right? So you don't need to memorize this one. Know this one, you can get them all, okay? Now, let's do something very similar. Can I erase that? Or parts of it? I'm doing it, okay? This time, guess what we might try doing? Not dividing by cosine squared theta, but dividing by sine squared theta. And what's sine squared theta over sine squared theta? Second? 1 plus, what's cosine squared theta over sine squared theta? Cotangent squared theta. And what's 1 over sine squared theta? Cosecant squared theta. And there's that one, just as written. I don't know why it didn't write, but okay. Just as written. Okay. Now, let me suggest something else to you. Different ways you can write these. You could subtract the cosine square from both sides and have sine squared theta is 1 minus cosine squared theta. Okay? Demetric is here. Well, if I could get in the right classroom, that would be better. I know you're in here, but hiding. There you are. And is it Caitlin? Huh? Serenithia? All right, sorry. You sound like you got a cold. Sorry. Okay. You can't yell at me today. No, okay. All right. Any questions so far? Okay. So you can rearrange this and have it sine squared is 1 minus cosine squared. When you have that, then you can take the square root of both sides and have sine is equal to plus or minus the square root of 1 minus cosine squared. Okay, that's not right with that pen. Stephanie's here. Okay, if I'd looked in the right class, I'd find you. There you are. All right. Anyone else? Come in since the call roll. Okay. Or you could subtract sine squared from both sides. Have cosine squared is 1 minus sine squared theta. Or take the square root of both sides of that and have cosine theta is equal to plus or minus the square root of 1 minus sine squared theta. Wait a minute. What's this plus or minus stuff? Can you have two different answers? That's the one I just said. Cosine theta is equal to plus or minus the square root of 1 minus sine squared theta. Okay? What's the deal with this plus or minus? How do we know which one to use? Or do we use them both? What do we do here? Figure out where you are, Waldo. And if you're in the first quadrant, which one do you use? Positive, because cosine is positive in the first quadrant. If you're in the second quadrant, negative, because cosine is negative in the second quadrant. If you're in the third quadrant, negative again, because cosine is negative in the third quadrant. If you're in the fourth quadrant with theta, 5. Oh, I get that. Okay. All right. Yeah. What's that? Yes, exactly. And since brothers split out 2 to 1, let's even them up. Okay, then you can take this one, and you can right now take a square root of both sides and have plus or minus the square root of 1 plus sine squared theta, and again, determine whether you use plus or minus by what your angle is, and whether secant is positive or negative in that quadrant. Okay? Or you can subtract 1 from both sides and have tangent squared theta is equal to secant squared theta minus 1. There's another Pythagorean identity. And you can take the square root of both sides of that and have tangent theta is plus or minus secant squared theta minus 1. Determine the sign by where you are. This one, take the square root of both sides, or subtract 1 from both sides, take the square root of that. There's lots of different ways you can write this. Okay? And they're all fairly easy to get from that basic one. This is the one I remember. This is the one that I use the most, but all the rest of them are valid too. So get used to them. You'll use them, all of them, a lot. Okay? So get to know them. Any questions? All right. Now they do that one little blurb at the bottom. Let's see if they do it on the slide set. Yeah. Note that sine squared theta, which to me is an easy way to express it, represents sine of theta squared, is the function squared. And that's what? The function squared. Okay? Cosine squared represents cosine squared. Put cosine of theta squared. So it's just easier to write it this way than having to put parentheses and whatever. You don't want to write this cosine theta or sine theta squared without anything there, because then it looks like you're squaring the theta, because you do, please excuse my dear Aunt Sally, whatever she did, and you would do the exponent first. So with parentheses, that tells you to take the sine of the angle, then square it. And that's what sine squared theta means. Square the sine, not the angle. All right, so I think we're ready for example 5. Here it is. Let theta be an acute angle such that sine theta is equal to 0.6. So find the values of cosine theta. Can you do that? How? Given what the value for sine theta is. Anybody have an idea? Oh, I erased it, didn't I? Oh, no, I didn't. There it is. Right there. If you know sine theta, which they told us, Here's how you get cosine theta. Right there, Pythagorean identity. Pythagorean identities relate sines and cosines, tangents and secants, cotangents and cosines. So whenever you know one of those pair, you can figure out the other. So let's go back and tell me. Well, then what would be cosine theta? Oh, how soon we forget. Okay. What would it be? Help me, somebody. Do I need to go? Second? Okay, you could put plus or minus. The square root of 1 minus. Got it so far. What's next? Sine theta. Sine squared theta. Yeah, sine squared theta. All right. Now, before we go any further, what about that plus or minus? Second? Why? Yes, it's an acute angle, which means you're in the first quadrant. So we don't need the minus sign. We can deal just with the plus. In fact, I can erase them both, because if you don't see either one, you assume it's positive. Okay? And now, at this point, all you do is plug and chug. Okay? It's the square root of 1 minus, and what sign? 0.6. So it's 0.6 squared, which would be, let's write it on down here, the square root of 1 minus, what's 0.6 squared? 0, say again? Say again? You probably said it right, I just can't hear well.
I guess 0.36.
0.36, because when you multiply a decimal, a point, you know, one decimal number, you have to get a 2, yeah, by itself. Okay, 1.36, and what is 1 minus 0.36? Oh boy, high level math here. Say again? 6 what? 4, perfect. Does anyone know the square root of 0.64? That would be 0.8. Perfect. Okay. And that's it. Now, was there a slightly easier way to do this? Remember our 3, 4, 5 triangle? We ran into that before. Well, 0.6 is 0.2 times 3, and 0.8 is 0.6 times 4, 0.2 times 4. So yeah, we could have just said, oh, that's a 3, 4, 5 triangle. Know what sine is, know what cosine is, yeah. Because they're opposite, yeah, whatever. Okay, so there's the cosine of theta. How about the tangent theta? Can we do that? What in the world is tangent theta? Exactly, sine theta over cosine theta. I call that the ratio identity. They call it the quotient identity, I think. Okay, whatever you want to call it. And what's sine theta? 0.6. And what's cosine theta? 0.8. And you can move your decimals one place. That would be 6 over 8, which is pretty exciting stuff, isn't it? 3 over 4, which you could write, since the other was written as a decimal, 0.75. Okay? All those are correct answers, but either one of them. Okay? So not bad at all, is it? These identities are really, really helpful. You can figure out a lot of stuff from them. Make sense? You look skeptical about that one, huh? Okay. Get to know them. They are really, really, really useful. Okay. You know how you get to know them best? How did you ever learn your name? They kept yelling at you, didn't they? Okay? Or you kept using it. How did you learn your social security number? you filled out enough forms until you knew it. So guess how you get to know these? Use them, and use them, and use them. And after a while, they're old friends. Okay? Of course they are. All right, everybody got that? Let's clear this and see how they do it. To find the value of cosine theta, which is a part asked for, use the Pythagorean identity. Sine squared theta plus cosine theta is equal to 1. We did use it, but I had you use it in a modified form. And so they plugged in a 0.6 and squared it, plus cosine squared theta is equal to 1. And then they subtracted that from both sides before they did the 0.6, which is fine. Cosine squared theta is equal to, they skipped a step there. 1 minus 0.36 is 0.64, exactly what we did. And then they took the square root of both sides. And they only did the positive square root. Why? Why? Because it was acute angle, and that's in the first quadrant, so cosine is positive there. So we forgot about the minus. So square root of 64 is 0.8. Okay? The B part of the problem, since you know sine, you just figured out what cosine is, use that to get your tangent. Sine over cosine, they're using another identity, and that's 0.6 over 0.8, which is 0.75, or 3/4. Any questions? Pretty easy to do, right? All right. I wish I could make it harder, but I haven't figured out a way to do so. Okay, so we're stuck with it like it is. All right. Now, or you could have done this and said, oh, well, I know that the sine of theta, which they gave us, is opposite over hypotenuse, some old hen, okay? So that is 0.6 over 1. And this is the same. If I multiply that, or maybe divide that by 0.2, I'll get a 3. And divide that by 0.2, I get a 5. And that would then be a 3, 4, 5 triangle. So multiply the 4 by 0.2, and you get a 0.8. That's another way to do it. That's probably not so easy. So that is another manifestation of your 3, 4, 5 triangle. Okay. Good deal. Or, once you saw that, lots of ways you could do it. Pythagorean theorem, without even thinking of 3, 4, 5, that does it for you too. Okay. Now, that was example 5. They're skipping example. Oh, there is a checkpoint at the bottom of the page. Please do that. Okay. They're skipping example 6, so let's go back and do example 6. Oh man, my head is closing in on me here. Let theta be an acute angle. Okay, got that down. Such that tangent theta is equal to 1/3. This time they're starting out with tangent theta is equal to 1/3. And you know that theta is acute, which means what? First quadrant is between 0 and pi halves, between 0 and 90 degrees, whichever you think of. Okay? Now, tangent theta is 1/3. Now, I know what they want you to do. Okay? I know exactly what they want you to do. Use the identities. But man, this is just set up to draw your little triangle. Okay? And we know that tangent is what? Is what? What'd you say?
1/3.
Okay, it's 1/3. Yeah, I got it. And what is tangent though? Opposite over which? Adjacent, exactly. Taking oats away, remember? Or dripping on acid. Okay, I knew you would do that one. Okay, so this is your angle theta, because this is your opposite side 1 and your adjacent side 3. Okay? Now, as soon as I see this, this is what I think. Now, can anyone come up with what the hypotenuse is then? Square root of 10. Perfect. Okay? Because 1 squared plus 3 squared will be your c squared there. Well, that's 1 plus 9 is 10. Square root of that is root 10. Okay. Now that we've got that done, and this isn't how they wanted you to do it, but I think this is the easiest way. Let's do the value of cotangent. Oh, we didn't have to do that. Why didn't I read the problem? What is, and here's Lindsay. Okay. All right. We didn't have to draw the picture for this. What is cotangent of theta? Second? Yes, it's 3 over 1 because it's reciprocal of tangent. So we didn't need our picture for it, but we could have used it for it. Why didn't I read the problem first? But then it asked for secant of theta. This is the A part. The B part is secant of theta. Now, I know what they wanted you to do was Pythagorean identity, but guess what? We use Pythagorean theorem to get this, so we're in the same place. What is secant theta defined to be? Hypotenuse over adjacent. So in this case, what would that be? Root 10 over 3. Just write it down, okay? Or you could have done the square root of 1 plus tangent squared theta, because secant squared is tangent squared plus 1, so take the square root of both sides. And doing that is work, but you could do it. You would get the same answer. Okay. This is so much, to me, it's easier. Any questions on that? It says using trigonometric identities, but guess what? On a test, I'm grading the answer. I'll look at your work, but if you got the right answer, you did it correctly, you're going to get credit for it. All right, there is a checkpoint after example 6 as well. Any questions before we move on to example 7? Any? Okay, let's do example 7. All right, to erase this. Yay? Okay. Example 7. Use trigonometric identities, or any way you can do it, to transform the left side of the equation into the right side. And these are all going to be angles between 0 and pi halves. So these are all acute angles. So here's the A part. Sine theta times cosecant theta is equal to 1. Okay. Now, we're going to do identities out of our ears, or some other body part, for in the next chapter. Okay? But they're giving us a preview of them now. Okay? Now, when I go to do these, I follow a certain few rules. One of the major ones that I do is I can't think of anything else to do, change everything to sines and cosines and see what happens. So sine is already in sine, okay? Leave that alone. What is cosecant in terms of sines or cosines? Yeah, so this will be sine theta. Leave that alone. And cosecant theta is 1 over sine theta. And goodness gracious, look at that. It's equal to 1. As long as theta, sine theta is not 0, and we'll assume we're not going to have that happen. Oh yeah, it's between 0 and pi halves, not counting 0 or pi halves, so yeah, that will be good throughout. Okay, let's look at the B problem. Any questions on that? Pretty straightforward. Ooh, okay. That was pretty straightforward. Let's look at B. Here is cosecant theta. I can't write. Oops, wrong one. Yeah. Okay. My pen is really slow too, so I can't tell exactly where I'm writing. Cosecant theta plus cotangent theta times cosecant theta minus cotangent theta. And they claim that's equal to 1. Goodness, they're stuck on 1, aren't they? Now, there's 2 ways you can proceed with this one. One way is what I just said. Change everything to sines and cosines. You're going to have a bunch of fractions here. I know you love your fractions, and they're not going to be bad, but there is another way. What's another way you could do this? Yes, why don't we FOIL it? Because this is sum times the difference of the same two entities, which basically we call a conjugate of each other. One thing multiplied by its conjugate. So what will that give us? Anyone know off the top, or we can FOIL it? You want to FOIL it? You said it's what? Cosecant squared theta minus cotangent squared theta. Because the sum times the difference, same two numbers, is going to be the difference of their squares. Now the question is, now we don't know that it's equal to 1, so I'm going to put question marks there. Is that equal to 1? Okay? Well, where have we seen those two together before? One of your Pythagorean identities, but none of them look just like that. How did it look? We had 1 plus cotangent squared theta is equal to cosecant squared theta. So if we were to subtract the cotangent squared theta from both sides, guess what we get? 1 is equal to cosecant squared theta minus cotangent squared theta. So yes, we get 1 equal 1. That's true in most cases. Okay. So sure enough, that's how we go on that. Oh, you can look in the book, and they actually do the FOIL method and then cancel out the cross terms, which we just sort of skipped because we knew what that was going to produce, and we saw from the Pythagorean identity that is indeed equal to 1. And there's a checkpoint there. Oh, yes, ma'am.
Quick question.
Okay. Okay, just a second. Let me pause this. Okay. I guess they're planning to cripple me. The ADA people are here, and they want to make sure my door is wide enough for me to get a wheelchair. So they say, do they know something? I don't know. Okay, we'll go on from there. Okay, that's what that was about. All right, there is a checkpoint bottom of the page. Please do it. Any questions on this? See how it works? Okay. Now we're ready for, these were the last one, applications involving right triangles. That's what we love. How do we use this stuff? Many applications of trigonometry involve a process called solving right triangles. Okay. Since you came in with, just snuck in with her, you're trying not to get counted, okay? But I caught you. Okay, Ryan's here. Is anyone else snuck in that I wasn't looking? I think we got them all. Okay. Many applications by solving right triangles. What do we mean by that? Well, you know something about every right triangle. What is that? You probably know several somethings. Name one thing you know about a right triangle. Second? Pythagorean theorem holds, that's true. Something about a length or an angle. One of the angles has to be 90 degrees, or pi has, because it's a right triangle. It's got to have a 90 degree or right angle in it. So you know one thing already. Now you know something else about the other two angles. No, they don't have to be 45. They what? Okay, the sum of the three for any triangle is 180, so you know that. But if yes, they have to add the 90, and we call those two angles. Second?
Acute angles.
They're both acute angles, absolutely. And what kind of special acute angles? Second? If they add to 90 or pi has? They're complementary angles of each other. So you know a lot of things about a right triangle. You know one of the angles is 90. The other two are acute angles that are complementary to each other. And you know something about the lengths, that the lengths obey Pythagorean theorem. Okay. In this type of application, you are usually given one side of a right triangle and one of the acute angles. And guess what? You are asked to find either one of the other sides, or given two sides, you're asked to find one of the acute angles. Hey, since you know one, all you need is two other pieces of information, and you got it not. Except, if you know the three angles, you don't know any of the lengths, because that could be a little triangle or a huge triangle. So you usually need to know one length and either another length or one of the angles. And then you can find all the rest of them. Because you already know one. Okay? So you can always do it. So in example 8, the angle you're given is called the angle of elevation. Now this would be like if I were out here surveying or doing something else. Let's say that I was estimating the height of that oak tree out there. Now I'm too high now because I'm not but if I was down on that level, I was estimating its height. The top of it would be, this would be the angle of elevation between the horizontal and the top of the tree. Looks like there's some mistletoe in that tree. So how high up is the mistletoe? That's what we're on. Okay. The angle of elevation. That represents the angle from the horizontal upward toward an object. Now there is a reverse of that. If I was looking down here and seeing somebody's car in the parking lot, and the parking lot's below me, then that angle would be the depression. Okay, the angle of depression. Okay, and I think that's on the next slide. Let's see if it is. Yes, the other applications may be given the angle of depression, which represents the angle from the horizontal downward to another object. Okay, the angle of elevation, all of them from the horizontal, which is usually where we measure angles from, positive x-axis. Angle of elevation is up, angle of depression is downward. Okay? These are just two ways that you could use angles to solve some real problems. Okay, a surveyor, here's a surveyor, standing, this is example 8. Yeah. Standing 115 feet from the base of the Washington Monument. It's shown in this figure. Okay, it's a pretty tall monument. 115 feet is not very far away from the monument. That means it's pretty tall. Okay, shown in the figure. The surveyor measures the angle of elevation to the top of it to be 78.3 degrees. How tall is the Washington Monument? I have no. Do it on your telephone. How would you do it? Alexa, how tall? No, never mind. Okay. This is how we used to do it before we had smart speakers. Never mind. Okay. How would you do this? Here's your picture. Oh, the one assumption here, and if any of you have ever been to Washington, D.C., you'll know it's pretty close to being flat. There are some hills, but they're not very great. But the mall, pretty flat. So there, and the Washington Monument is not from Pisa, Italy, so it doesn't lean. It's pretty much straight up. So we assume that we do have a right angle here. Okay? Now, what we're looking for is y. How tall is the monument? We have the right angle here. We know this angle from horizontal to the top is 78.3 degrees. So how in the world, oh, and we know the distance from the base to that point is 115 feet. So how could we determine the height? Here's the angle you know. Here's the side you know. Here's the side you're looking for. What trig relationship deals with this angle and that side and that side? How is 78? Say again?
Tangent.
Tangent, because this is the opposite side, there's the adjacent side. We aren't at all concerned with the hypotenuse in this problem. So then, what sentence can you write down? Tangent of 78.3 degrees. Be sure you're in degree mode when you enter your calculator here. That's equal to what? Y over 115 feet. Okay? Now, we're wanting to solve for y, the height. That's what we're looking for. So we multiply both sides of the equation by 115 feet. That wipes it out there. 115 feet here. The units sort of get in the way. So here we have y is equal to 115 feet times the tangent of 78.3 degrees. Got your calculator? Make sure you're in degree mode, and then go to town mode. See what you get. Anybody?
Approximately 555.
Say that again?
Approximately 555.
555 feet. Okay. Good estimate there, because you're given 3 digits here, 3 digits there, so I wouldn't do it any more precise than 3 digits there. And 555, yes, that's what they got as well, 555 feet. And you can ask Siri if that's right or not, you know, whoever. Okay. All right. There is a checkpoint following that. Certainly welcome to do that. Oh, let's see how they did it. Oh, I think I can just go to the, yeah. From the figure, you can see that the tangent of 78.3 degrees is the opposite side over the adjacent side, exactly what your reasoning was. The opposite side being y, the adjacent side being x, though we didn't call it x. I don't guess they called it x. But we called it 115, where x equal 115 and y is the height of the monument. So the height of the monument is x times tangent of 78.3, which is 115, times the tangent of 78.3 in degree mode is 4.8 blah, blah, blah. They used a lot of digits there, and they came up approximately 555 feet. Good deal. Any questions? And that is followed by a checkpoint. So please do it. Now, I have a feeling. Okay. This skips example 8. So let's go back and do example 8. No, I'm sorry. 9. Example 9. Sorry. I can't read. A lighthouse is 200 yards from a bike path. The bike path is along the edge of the lake. Because when I first read that problem, a lighthouse is 200 yards from a bike path along the edge of the lake. Well, was it the lighthouse along the edge of the lake? Well, no, the path. The picture helps, okay? So let me sort of draw the picture here. And this is one smooth lake shore, okay? Very straight line-ish. The bike path is even straighter line-ish, okay? I think I could even write on that one. It looks pretty flat to me, okay? And it says the lighthouse is down here 200 feet from it. So here, they don't draw the lighthouse. Thank you very much. So the lighthouse is here. This is lighthouse, okay? And this is 200 feet from, I think, is the bike path? Yeah. So this is 200 yards, 200 yards from the bike path. Okay. A walkway to the lighthouse, because of all the hills and stuff there, it looks pretty flat to me. Why in the world did they put the walkway there? I guess people needed more exercise. Okay? So the walkway for the lighthouse is 400 yards long. So this is 400 yards. Okay? The walkway. Find the acute angle theta between the bike path and the walkway. Well, that would be this angle. Not this angle over here. That would be obtuse. So they want the acute angle between the walkway and the bike path. Okay, so this is the angle theta we're looking for. Find that angle. Okay. Now, what trig function of this angle uses this and that? Two things you're given.
That's sine.
The sine does. Because the sine of that angle theta is equal to what? Opposite over hypotenuse. This is opposite. This is your right angle because it's that far from the bike path, so you assume that's perpendicular distance. So that would be 200 yards over 400 yards. By the way, your units always have to cancel out because a sine function, any of your trig functions are dimensionless quantities. So if one of those was in feet and one in yards, you better get them to the same unit so you can cancel them out. Okay? Don't just use any old numbers there. Okay? Now, can anyone do that math? It's pretty hard. 200 divided by 400? That's 1/2. Now here we have sine of some angle theta is equal to 1/2. Do we know any such angle that would be true for? Remember, there were some of those angles I said were going to be your close friends. Yes, that's going to be your 30 degrees. So your theta here is equal to 30 degrees. Or, if you're in radians, that would be, anybody? Pi 6. Perfect. Oh, and I forgot to say this. I've been supposed to say, I think I've said it before, but I'm supposed to say it repeatedly. Miss Gerasi, coach of the math team, is looking for good people to be on the math team, and there are not many better people than y'all. So, hey, give it a thought. Have any of you participated in that? You really, I think you'll find it useful. I know, Dimitri, you've worked with Miss Gerasi before, haven't you? She knows her math. And frankly, I'll give this example. I think I've probably given it before, but just give it. Have a guy who's currently in my Cal 3 class, but back when he was in Cal 1, when he first came into it, he was pretty hesitant. He was sort of scared of the prospect of calculus, and he was really uncertain seeming. But he did join the math team, and as the weeks went by, he was more and more confident, and soon he was answering the questions just about as soon as I could get them out of my mouth, because he was learning the math on the math team before we got to it in Cal 1, okay? It's a beneficial experience. And it's fun, okay? So please consider doing the math team. I think they meet Fridays, sometime late morning to early afternoon, Birmingham West Campus in C100. They will not be meeting this Friday because we have professional meetings in Tuscaloosa. That's tomorrow I'm talking about, in Tuscaloosa at Shelton State. So Mr. Rossi will not be there tomorrow, but subsequent Friday she will be. So give it a consideration. I think you'll find it. It's helpful and a lot of fun at the same time. Okay, any questions on this? Now, there was another way to do this, but we haven't hit it yet, and I'll hold off telling you another way to do this one. But we knew this one because we knew that relationship of that the sine of 30 degrees is 1/2. Okay, now that then leads to what was on the next slide. By now you're able to recognize, didn't you, that if the angle is theta, the acute That's the acute angle that satisfies the equation sine theta is equal to 1/2. That will work. Or theta equal pi 6, same thing. Suppose, however, you're given an equation sine of theta is equal to pi 6, and we're asked to find the acute angle theta. This isn't quite how you would do it, but this is how you could estimate it. You know that the sine of 30 is 1/2. We just did that. That's 0.5. Sine of 45 is 1 over root 2, which happens to be 0.707. Okay? So you know that the angle who gives you a 0.6 is something in between these two angles. Now, it looks like it's really close to being midway between them. It's not quite, because the sine curve is not a linear curve, it's a curve. Okay? So you can't extrapolate that way, but it's a good guess. Halfway in between that is 7.5 degrees, so about 37.5 degrees, maybe 38 degrees, because it's a little more. It's not exact, but it's not a bad guess. Okay? Right now they say guess somewhere between 30 and 45. And 38 is somewhere between there. And that's all they wrote here. All right. In the later section, we will determine how to get the exact value. Like I said, that's coming up. They skipped example 10, so let's go back and do example 10. Okay? How are we doing on time? We're okay, right? Yeah. All right. I think we can erase one more. Okay. Find the length C and the height B of the skateboard ramp below. So this time they're looking for two pieces of information. Here's our skateboard ramp. It's a 13-foot run with a B rise. Okay? Okay? And we know this angle here is 18.4 degrees. The other thing we're looking for is how long a piece of plywood do you need C for a 13-foot run and 18.4 degree ramp. How would you proceed? Good question to ask yourself. What trig relationship relates the angle over here? Oh, and by the way, the assumption here is you have built that square. So that is perpendicular. Okay? The question then is, what is the relationship between the angle 18.4 and either side B and side 13, and later we'll do C. Pick one of them to do first. Second?
Cosine.
Which
Cosine.
one? Okay, for which?
18.4.
For which?
18.4?
Okay, yeah, I know, but which, A or B or C? Which are you doing?
C.
C, yes, okay. If you're doing B, it would be cosine. Okay, so you're absolutely right. How would that go then? Cosine of 18.4 degrees would be what?
Adjacent hypotenuse.
Be what?
Adjacent hypotenuse.
Adjacent over hypotenuse, right?
Right.
13 over C. Perfect. How would you solve for C? And this, by the way, is feet. Say again? I can't hear you. Well, number one, I don't like C in the denominator. I mean, I really don't care for denominators that much anyway, but I sure don't want my unknown down there. So how could I get it out? Rescue me. Multiply both sides of the equation by C. Right? And that gets you out of the denominator. Okay? So now we have C times the cosine of 18.4 degrees is equal to 13 feet. Now we divide both sides by cosine of 18.4 degrees. Okay, that gets rid of it here, and that leaves the C by itself, which is a very good thing. Unless you're C, of course. Okay. So 13 divided by the cosine of 18.4. Be sure you're in what mode? Degree mode. Okay. And what do you get? Approximately. Anybody?
13.7.
Second?
13.7.
Okay, you got 13.7 feet. Okay. Does that sound reasonable?
Yeah.
Yes, the hypotenuse is always along the side. This side was 13. It's got to be longer than that. This is longer than that. So it sounds reasonable. Okay? How do we get B? Second? Pythagorean theorem. That's certainly one way to do it. Okay? Now, here's the only thing I don't care for using Pythagorean theorem there. Because we're going to have to use C for that, right? Well, C is a derived quantity. Number one, you probably rounded off. Did you? Yeah. So you have a little bit of round off error. And you, not that Jake would have, could have made a mistake. Well then, so then you'd be coming up with the wrong answer there. So if I can get away with it, I want to use the things I know are true. These two. So what would be an alternative way to get B? Why sine? Oh, but then you'd be using hypotenuse, which is again a derived quantity, which you could have made a mistake. Tangent! The tangent of 18.4 is opposite over adjacent. Yes, that's going to give it to me using things I know as precisely as we can know. So we know that tangent of 18.4 degrees is equal to what? B over 13, you said? Okay. And then to get B, what do we do? Multiply both sides by 13 feet. Okay? Wipes out the 13 feet on that side, and you get B is approximately equal to 13 times the tangent of 18.4. Any suggested answer? 4.3? Is that what you said? 4.3 feet. Okay. That seem reasonable? Well, let me give you, I think you know this already. This is, how is this angle related to that angle? The one up there. Yeah, they had to be 90. So which one of these are bigger as well? Yeah, that one's bigger, this one's smaller, by a long shot. So the side opposite the smallest angle is going to be the shortest side. That certainly is shorter than this or that. So yes, at least relatively speaking, it makes you feel warm and fuzzy, right? So we think we'll be okay there. Let's see what they got. They get the C, and they did it same order you did, 13.7 feet approximately, and they get the B, the rise, to be about 4.3 feet. Sounds good to me. Okay, there is a checkpoint, well worth your time to try. Okay, 4.3 exercises. Let's first do vocabulary. Match each trigonometric function with its right triangle definition. How are we doing on time, okay? Yeah, we got plenty of time. Okay, the A, B, C, D, E, F, and G, F and F are sine, cosine, tangent, cosecant, secant, and cotangent. And which of these match with which of the definitions? Which is sine? Sine is what? V, 5. That's 5 in Roman numerals, okay? So sine is opposite over hypotenuse. Cosine is what? 4. That's adjacent over hypotenuse. Tangent? 6. Opposite over adjacent. Cosecant? Cosecant is the reciprocal of sine.
So it's 3.
So that would be 3. Hypotenuse over opposite. Secant?
That's 1.
That's 1. Hypotenuse over adjacent, reciprocal of cosine, and cotangent, B, which is adjacent over opposite, reciprocal of tangent. Perfect. Number 2. Relative to acute angle theta, the 3 sides of a right triangle are the blank side, and the blank. Those same 3 words we were using in our Roman numerals up above. Adjacent side, opposite side, and hypotenuse. Excellent. Cofunctions of blank angles are equal. Second? Well, they all would be acute, but what specific ones? Complementary angles. Cofunctions, CO means complementary. Okay. Number 4. An angle of blank represents the angle from the horizon upward to an object. Angle of elevation. And whereas the angle of depression is the angle downward to an object. Okay, homework exercises here. Do any of the odds 5 through 9. They're all at Calc Chat. 5's at Calc View. Do either 11 or 13 or both. They're both at Calc Chat. Do any of the odds 15 to 21. They're all at Calc Chat. Do any of the odds 23 to 27. They're all at Calc Chat. 27's at Calc View. Do any of the odds 29 to 35. They're all at Calc Chat. Do any of the odds 37 to 41. They're at Calc Chat. 39's at Calc View. Do any of the odds 43 through 51. They're all at Calc Chat. 47's at Calc View. Do any of the odds 53 through 57. They're all at Calc Chat. Do either 59 or 61 or both. They're both at Calc Chat. And then the applied problems, you can do any of the odds 63 through, goodness gracious, 73. They're all should be at Calc Chat. Okay? There's an exploration, 3 true false. Any of the odds 75 to 79, they should all be at Calc Chat. You can think about doing 81 if you'd like, or 83, and that sort of wraps them up. Any questions? Okay. We still have more than 10 minutes, so let's move into 4.4. Any questions on 4.3 before we leave it? All right. All right, 4.4. And by the way, at the end of this section will be your first test. So I'll try to have that ready for you Tuesday, provided you're not out shoveling snow again Tuesday. Okay, so we will plan to have your first test on Tuesday. And remember, it is a take-home test if y'all want to do it that way. Is that okay? Okay. Okay. And we'll go from there. All right, let's get this slideshow set up from current slide. We're still in Chapter 4, Trigonometry. Good place to be. And 4.4 are trigonometric functions of any old angle. We're not limited to being acute angles anymore. Any angle. So, what we'll do first is evaluate trigonometric functions at any angle. We'll find reference angles, which will make the whole process a little easier, and then we'll evaluate trigonometric functions of some real numbers, which is what we've been doing anyway. Okay? When you see that, you're getting into radians. That's what they call radians, or real numbers. They are real numbers. So let's start with the introduction. Oh, have we seen this kind of stuff before? Not exactly, but awfully close. The definition of trigonometric functions were restricted to acute angles in the first quadrant. Okay? In this section, the definitions are extended to cover any old angle anywhere. When theta is an acute angle, the definitions here coincide with those given in the previous section. But now we're going to extend it to any. Okay? So, let theta be an acute angle in standard position, xy, at a point on the terminal side of theta, and r, no, I'm sorry, I said acute. Let theta be an angle in standard position with xy, a point on the terminal side of theta, and r is equal to the square root of x squared plus y squared. Okay? And that, by the way, is not equal to 0. Okay? Only way this could be 0 is if you were at the origin, and there you don't have any length at all. So we don't even mess with angles at the origin. Okay? From the origin, yes, but not at the origin. Okay? So this r is not 0, but it's also always positive. Okay? Now, when we're on the unit circle, what was that r? On the unit circle, what was that r? Y. So this is going to look just like your unit circle equations, only instead of 1, you put r. It's that simple. And what does this look like? Think Pythagorean. What does this look like? Where x is adjacent and y is opposite, this would be hen. What was yours? Hippie. Okay. Okay. Hypotenuse. So in the others we did r is instead of h. Oh, and of course y is instead of o, and x is instead of a. Because x is the adjacent side, y is the opposite side. Okay? Because you see, if you draw a little triangle here, or a triangle here, okay, wherever you want to call it, this is your hypotenuse. There is your angle here, and we'll talk about the angle over here later, but your x is your adjacent side, and the y is the opposite side. Okay? Y value would be here. Okay? So this is the same setup, only here we're using x, y, and r. Y is vertical, that's equivalent to opposite. R is equivalent to hypotenuse, x is equivalent to adjacent. All the same things. Okay? Remember, r can never be 0, so therefore we don't have to worry about dividing by 0 here. However, x's and y's could be 0, so you have to eliminate 0 from these denominators. Just can't have them be 0. There's the same things we used before. Sine is in unit circle with y by itself, right? Now it's y over r. Because that was y over 1. So it's y over r. Cosine was x. Now it's x over r. Because x was x over 1, unit circle. Tangent was y over x. It's still y over x. Cotangent was x over y. It's still x over y. Secant was 1 over x. Now it's r over x. The only difference here between this and your unit circle was everywhere that you either didn't have anything, put a 1 there, or where you had a 1, put an r there. Where you have a 1, put a r. And secant was 1 over x, now it's r over x, cosecant 1 over y is now r over y. Okay. Now they write the order differently just about every time, and I don't know why. I would like to do sine, cosine, tangent, cotangent, secant, cosecant. So you have the reciprocal ones across from each other. Now your reciprocal ones are here, here, and there, which is fine, but you know, why aren't they more consistent? Okay. Any questions on that? R, two things. Can never be zero and is always positive. Remember that. R is always positive. X and Y can be positive or negative. X is positive over here, negative over here. Y is positive here, negative there. R is always positive. Always positive. Never zero. Never zero. Okay. So, I think we're ready for example 1. No, we've still got to talk some more. Because R can never be zero, okay, it follows that sine and cosine functions are defined for any real value of theta, and we've already talked about that. However, when X is zero, then your secant and your tangent are undefined, because you can't divide by zero, and secant and tangent had X's in the denominator. Okay? So, not undefined there. For example, the tangent of 90 degrees, undefined, because there your X is zero. Similarly, Y is zero, cotangent, cosecant, undefined, because you see there, cotangent, cosecant have Y in the denominators. Okay. Does anyone need this any longer? Okay. All right, here's example 1. Do we have time for it? I think so. Okay, let's try. Let negative 3, 4 be a point on the terminal side of theta. Where are we, Waldo? Second? Second quadrant, because negative 3, you're on the left side of the y-axis, but you're above the x-axis, that puts you in the second quadrant. Let that be a point on the terminal side of theta. Find the sine. What in the world would the sine be? Let me get my pen back. Tell me what sine is. Okay. All right. We were doing opposites. Okay. Okay. Think of this as x, this is y, and then what in the world would r be? Okay, go again. What is sine?
Is y over r.
That's y over r. And what is, I know what the y is, but I don't know what r is. Oh no, we can't do this problem, can we? What's r? This is 17th letter in the alphabet. No. What is r? I just made that up. I don't know.
It's x squared plus y squared over.
The square root of x squared plus y squared. You're absolutely right. This is what r is. And that would be the square root of what? 9 plus 16, which is the square root of 25, which is 5. Plus or minus 5? Always positive, always positive. So this will be 5. So there we found what the sine is. What is a cosine? X over r, you're absolutely right. And what is that? Negative 3 over, which is 5. Okay, we don't have to redo it again. And what is the tangent of theta? Which is? Second? Yeah, negative 3, so that would be negative 4/3. Perfect, you did it. And you could come up with the other 3 trig functions, couldn't you? Cotangent would be negative 3/4. Secant would be negative 5/3, and cosecant would be 5/4. Right? Done. All right, good deal. There is a checkpoint there. Please do the checkpoint. All right. Oh, let's see how they did it. Since we have time. I hope we do have time. Referring to the figure, they drew the figure here. There's a point negative 3, 4, negative 3 on x, 4 on y. R we know is the square root of the square of those, sum of the squares, which is 5. And now we can just write them down. Sine is y over r, 4/5. Cosine is x over r, which is minus 3/5. And tangent is y over x, which is minus 4/3. Done. The signs of the trigonometric functions in the four quadrants can be determined. Is it time? Okay. Second? 3 more minutes? Okay, let's do this slide. Huh? Two. We can do this slide. If we do it faster, can we? Yep. Okay. All right. The signs of the trigonometric functions in the four quadrants can be determined from the definitions of the functions. You know what they are, right? Okay. Cosine x over r. Guess what? You really don't have to think too hard. R is always positive. X is negative over on the left-hand side. So that means the second and third quadrant, cosine is negative. First and fourth quadrant, they're positive. Cosine is positive whenever x is positive, which means on the right-hand side, first and fourth quadrant, and r is always positive. Okay? So here's the picture. X and y's are both positive here. X negative, y positive, both negative. X positive, y negative. So all functions are positive here. Sine and cosecant positive here. Tangent and cotangent positive there. Cosine and secant are positive there. So all students take calculus. Okay? All state technical college. However you want to remember this. Those are the sine, cosine, and tangent. Remember, everything positive here. Only 2 of the 6 are positive here. 2 of 6, 2 of 6. Okay? And you just remember it's the main 3, one of the main 3 plus its reciprocal. All right. Ooh. Next time we're going to have to start with example 2 because they don't do example 2. So we'll start there. Let me erase this. I think I erased it sometime in the past. Oh! I know y'all want some homework exercises. Yes. You can do any of the, either 9 or 11, or both. Okay? And you can do any of the odds, 13 to 17. You can do 19 or 21. And we'll stop there. Do the rest of them later. Have a great weekend. Of course, doing trig will make it a great weekend, right? Yes. And we'll see you Tuesday, I hope, and I'll give you your test on Tuesday. What's that? On the first 4 sections. On Tuesday. Yeah, we have 2 tests in chapter 4, and each of the others are 1 each. 4 is such a long chapter. I knew you didn't want to go so long without having a test. So, yeah, exactly. What's that? Yeah. All right. Good deal. Have a good week.